This lesson we're going to cover some topics that we either skipped over or didn't go into as deeply as we should have originally. So the first thing we're going to recall was inverse functions. Remember, the inverse function is a function that undoes itself, but really when we looked at inverses, they changed the input and the output. So they switched the domain and range of each other. So if I'm using a graph, like the graph of f of x, if they want me to find the inverse f of negative 1 of 12, that really means the input of the inverse is the output of the original. So we're looking at the graph to find when y equals 12. So I'm looking at the graph and I see y is 12 here. Therefore, f of x would have been 20. Or our answer would have been 20. All right, f of negative 1 of 12 equals 20. So you go ahead and try this next one. Use the graph of f of x to find f of negative 1 of 65. Pause it and then you can check your answer. All right, so here we get 4, because when I find the y value of 64, it had an x value of 4. So we could also do this from a table of values. We could do it not just from a graph, but a table of values. So here, if I want to find f of negative 1 of 4, again, I'm looking where is y equal to 4. And I find y is 4 right here, so that means my answer is 2. All right, they're always going to try to trip you up by having the number 4 appear twice. So because we're saying the inverse of 4, we're looking at the output of 4. So another word that we didn't talk about is called invertible, and it's based on the word inverse. So invertible is when a function's inverse is also a function. So that means it could pass the vertical line test. So if you recall, the vertical line test is if you had a function and you tried to draw vertical lines on it, it only crosses the graph once. And there are some graphs, when they're drawn, that, let's go same colors I just did. When I graph the vertical lines, they hit the graph twice. So this is not a function because it doesn't pass the vertical line test. So we have to look at the shape of our original figure and figure out if we were to flip it along the line y equals x. If you recall, the line y equals x was here. If I were to flip it over that line, would it still pass the vertical line test? So here we already have them graphed. The red function is the original and the blue is its inverse. So we'll focus on the inverse. Does it pass the vertical line test? And no matter where I draw a vertical line on that blue line, it only touches it once. So yes, this red function is invertible because the inverse is a function. All right, I'm going to write that out. It is invertible, yes, because the inverse is a function. I'm not going to ask you to explain, but I'm just putting why, so you know. So let's look at a few more, right? So that was a linear function. All linear functions, when I do that, will work. Here I have a cube root, a cube root function, right? This is my function over here in red, and when it's flipped over the line y equals x, we get this blue line. So if I checked the blue line, no matter where I put that vertical line, it only ever touches the graph once. So this is, again, yes. The function in red is invertible because the inverse passes the vertical line test. In this example, I have a fourth power function, a quartic function. So here in red is my quartic function. When I flip it over the line y equals x, notice now it touches it twice. So this is no. The red function is not invertible because the inverse does not pass the vertical line test. The inverse is not a function. Let's look at some where we only have the one function. So here I have a square root function, and if I were to graph the inverse of this, I know that it switches x and y. So if this was 4, 0, we're going to go 0, 4, and then it went towards the line, so it's going to go towards the line. So this is the inverse, and now we could check the vertical line test. Only ever touches it once, so that is yes. So the square root function passes the vertical line test, so that works. Here we have a quadratic. If I were to graph this, right, we're at negative 4, 0, so we're going to go 0, negative 4, and then we're going to go like this. And I could see already that it does not pass the vertical line test, right? It touches at least twice every time. So this is no. And now I have a cubic. So let's switch every x and y. So negative 4, 0, we'll do 0, negative 4. Negative 2, 8, we'll do 8, negative 2. And negative 6, negative 8, we'll do negative 8, negative 6. So this is going to be something like this, which will pass the vertical line test at every point. So that is yes. We could also look at them in terms of equations. So generally speaking, our cubic functions will work. If it was more advanced than the transformation of x cubed, then it might not work. But for now, we're just looking at the transformations of these main functions. So they're all based on the parent function. So cubic, yes, works. Squared, we already saw squared was like this. So when I flip it like that, that doesn't work. So that's not invertible, right? This one was like this. So when I turn it like that, so that's fine. Square root went like this. So the inverse goes like this. So that works. Cube root, oh, that's a bad picture because that makes it look like it's straight there. Looks something like this. So its inverse is something like that. Passes the vertical line test, so that works. Negative 3x to the fourth is going to be more like this. So when I flip it over that line, we go over here. And now this does not pass the vertical line test, so that's also not invertible. So really, we're focusing mostly on even roots are not invertible. Odd roots will sometimes be not invertible. Sorry, I keep calling them roots. Odd powers. Even powers. Let's fix that up. Or where we're going to look at not invertible. The other thing with invertible functions is if you were to restrict the domain of the inverse, it could turn into a function. So if I were to look at this, which intervals are not suitable to make it an invertible function? So really, because x squared minus 3 is symmetric along the x-axis, right, or it changes direction along x equals 0, y-axis, x equals 0, then anything to just one side or the other will work. If I have any combination of points on both sides, then I'm going to end up having the same y values appear, which when I make the inverse, I'll have the same x values appear, and that doesn't work. So here, negative 5 to 5, I have some negatives, some positives, so that is not suitable. This is negative infinity to 0, so that's only negative numbers, so that's fine. This is negative infinity to positive infinity, so it has negatives and positives. That's not going to work. That's not suitable. Here's 0 to infinity, so it's only the positives, so that works. Negative 1 through 4 has both negatives and positives. That's not suitable. And 6 to infinity only has positive numbers. It starts at 6, that's fine, but it's still only positives, so that one works as well. The other topic, which we didn't get to chat about much, was average rate of change. And really, when you're doing the average rate of change, you're looking at the slope over a specified interval. So remember, slope is y sub 2 minus y sub 1 over x sub 2 minus x sub 1. Change in y over change in x. So if I look at it in terms of a table, they're telling me what is the average rate of change over the interval from x equals 1 to x equals 3. So I'm looking at these 2 points. That's my x1, my x2, my y1, my y2. So I'm going to find the slope. Y2 minus y1 is 250 minus 10. X2 minus x1 is 3 minus 1. So that's 240 over 2, or 120. And that would be my average rate of change over that interval. So you go ahead and try this one. Find the average rate of change over the interval from x equals 3 to x equals 6. Pause it and then check your answer. All right, so when I do 50 minus 14 over 6 minus 3, we get 36 over 3, or an average rate of change of 12. I could find the average rate of change not just from a table, but also from a graph. So they want to know between which 2 points is the greatest average rate of change. So really, you would find the slope between every pair and compare those. So between 2 and 1, it's 70 minus 40 over 2 minus 1, so 30 over 1. 1 to 2, 30 over 1 is 30. Then 2 to 2.5. We have 80 minus 70 is 10. 2.5 minus 2 is 0.5. So 10 over 0.5 is actually 20. So it's 30, 20. Then we have 2.5 to 3. So 86 minus 80 is 6, or 3 minus 2.5 is 0.5. So 6 over 0.5 is 12. Then I have 92 minus 86 is 6. Over 5 minus 3 is 2. So 6 over 2 is 3. And then for my last one, from 5 to 9, 96 over 92 is 4. 9 over minus 5 is 4. So 4 over 4 is 1. So the greatest rate of change actually happened between 1 and 2. And that is everything that we needed to cover in order to get everything done for the final.